Hello everyone. So we are dealing with the extreme value theorem today, and it says that if f is such that in the closed interval a and b tends to the set of R is continuous, then f assumes its minimum and maximum. So the extreme value theorem is something you need to understand the function the way it is stated. And when dealing with the extreme value theorem, there are two things you need to take into consideration. First thing is the interval we're dealing with must be closed as stated here. So in this case, our interval is AB and it is a closed interval. And secondly, our function must be continuous. So this has been stated in the question, and which is what we are going to use in selecting which function applies, the extreme value theorem applies to. So option A says that the theorem applies to our function f such that in the closed interval 0 and 4, as it tends to the set of real numbers, f of x equals to e to the power sign x. Now we have to take note of this. We have been told that our function is e to the sign x and the interval is 0, 4. So the first condition is it's a closed interval, right? Our interval is a closed interval. That's the first thing we've noticed. And here is a function given to us. So we have to check, is this function continuous? And when they talk of a function being continuous, what do you understand? If a function is continuous, meaning that you can sketch or draw that function on a paper or on a board without removing your pen or your chalk, depending on where you're drawing. So that's a continuous function. For instance, sine x, if we have our function f of x to be sine x, generally when we draw the sine function, it's a continuous function because it continues to infinity. We can draw the sign without actually removing our pen. And same thing with our exponential function. If I'm not mistaken, our exponential function is something of this form. It's something of that form, and it's a continuous function because it starts from negative infinity to positive infinity. You can draw this function without necessarily removing your hand on the plane or on the board, within the set of the real numbers. So that's an example of a continuous function. So in this case, if you have two continuous functions, that is the exponential function e to the power x, e to the sine of x, that is an exponential function, and sine x, a trigonometric function, that are both continuous. Therefore, combining two continuous functions, they will all be continuous. So in this case, the two conditions are applied. Therefore, this option A, the extreme value theorem, applies here. So the extreme value theorem applies to that function. Now the second option says that the theorem applies to f such that from 0 and 1, as r tends, and from 0 to 1 in the set of R, as f of x tends to 1 on x. So the first thing we notice is this is not a closed interval. This is not a closed interval. So without thinking too much, you can cross out this option without even looking at option B, like without checking if it is a continuous function or not. Let's check if it's a continuous function. We have our function to be f of x to be 1 on x. This is not a continuous function because if you look for the vertical asymptote, x will be equal to 0. This is a vertical asymptote. It is discontinuous at this point, right? If you sketch this point, there's going to be a vertical asymptote that will cause the function to tend to infinity. So you can't draw this function without removing your hand, basically. So this is a discontinuous function. Now, if we look at the next option, it says that the theorem applies to, yes, we have been given a closed interval. That's true. Now, but this function is not discontinuous from the previous explanation. So this option is equally wrong. And D, option D, says that the theorem applies to f such that R tends to R. Here, when you talk of R tending to R, right, basically we are dealing with a set from negative infinity to positive infinity, and this is not a closed interval. So these are open intervals, right? It's open, and the theorem only applies to closed intervals. So this option is equally wrong because it's true that our function f of x is continuous because it's an exponential function, and all exponential functions are continuous functions. The next option says that R tends to R. Again, this is not correct because the set of R is an open interval. And the last option, F, says the theorem applies to F such that in the interval 0 and 1, first of all, this is a closed interval, right? Secondly, we have been given our function d, so the first theorem holds. Let's check if this is a continuous function. We have f of x to be x squared plus 1 divided by x squared plus 2. So this is our function. We want to check, is this function a continuous function? Yes, this is going to be a continuous function, and one easy way to check is to verify if it has a vertical asymptote. And to check that, we can say x squared plus 2 should be equal to 0. So x squared should be negative 2, so x will be the square root of plus or minus the square root of negative 2, which is in the complex plane, right? So this is like the square root of minus 2 the square root of minus 2, and this is in the complex plane. So the vertical asymptote does not exist, therefore it is a continuous function. That's an easy way to verify if the vertical asymptote exists, right? Therefore it's not a continuous function. In this case, it doesn't exist, therefore it's a continuous function, and this is a rational function, and we can draw this function without removing our hand on the plane. So that's a simple way in which you can verify if the theorem applies to a function or not. So that's it for this question, and if you're interested in getting more, make sure to subscribe and turn on the notification, and see you in the next video.